Hi, Young and Freedman have a fun little topic tucked into the end of Chapter 10 of their book, University Physics. Of course, physics isn't just the property of one textbook, and so you may find a section on gyroscopes and precession in your physics textbook too, but maybe not. This is not, I don't think this is treated in every physics textbook, but a gyroscope is basically some sort of a mechanism that spins in two different dimensions. So in the gyroscope that Young and Freedman uses their model, you have a kind of a pivot here and then a flywheel that spins here. And precession is the fact that as this flywheel spins and rotates, then it begins to spin in the other dimension as well. So if this is the y dimension, then it begins to spin in the the x or the z dimension, if you would, x and z. Well, x and z, isn't it? It's a three-dimensional kind of thing going on here. So anyway, believe it or not, we could also use a spinning top as our example here. For example, if we were to take this picture and rotate it to where this flywheel was the top of the top and the pivot was the bottom of the top that's touching the table, say, or the floor, then we have a similar situation. You know how sometimes tops wander around the floor or a top wanders around the table? That's a kind of precession dynamic that comes from the forces and torque associated with spinning the top. So this would apply to tops, and I've seen tops discussed under this section in other physics textbooks. But we're going to use Young and Freedman's sample of a gyroscope. Okay, so Young and Freedman start off by saying, if the flywheel's not spinning, then of course it's just going to fall to the ground under its own weight. But an interesting thing happens, because if you have that force of weight pulling downward, then you have that's kind of a circular situation. You have a pivot, and there's a circle, or I suppose from your point of view, a circle this way, where the axis that the flywheel's on falls to the ground. That's an arc of a circle. And so you have a torque situation here, where you have the weight force downward, and you have an R. So R cross W gives us a kind of torque, as it were. And if you use the right-hand rule, as we do here, then you can see that the R cross W is going to exert a force in this direction. If you use the right-hand rule. So if you take your right hand and you start, I think this is the way it's going to be from your perspective looking at this video. So if you take the R coming out and you curl your right hand downward toward the weight, then it's going to point in this direction, which you can see here. R cross W, the cross product, is going to torque it in that direction. And so even as it falls, there's going to be a tendency for it to want to move, the axis to move in that direction. Now, if we rotate the flywheel, if the flywheel's rotating, then that force begins an angular momentum going. From your perspective, I think it's this way. So what happens is, as the initial angular momentum, L initial, pushes this way, but then if it's spinning, then we have the torque that pushes it in this direction, and it begins to precess in a circle like that. And that's the fun. I mean, it's somewhat counterintuitive that it would do this, but it does. It works. That whole cross thing with torque. If you're like me, when you first came across the idea of a torque and the right-hand rule, you might have thought, that doesn't make any sense at all. Well, here, with the gyroscope, you can see that it actually happens in real life. That if you have a flywheel here, spinning, then it's going to start precessing around here. It's going to, as if magically, stay elevated as it goes around. And tops, of course, do this as well, and of course they wander around often. And so that's called precession, that rotating tendency. By the way, I was watching the movie The Martian on video this weekend, which dates when I made this video. But during the movie The Martian, they tried to launch a supply rocket to Mars so that the astronaut that was stuck on Mars could have food supplies, in 300 and some Martian days. And the supply rocket blows up. They didn't have time to do all of the security and safety tests. And if you listen to that movie, go rent it. What makes it blow up is precession. It develops a wobble, which means that it begins to turn like this, and that causes the rocket to explode. And so precession is real. The Earth, I didn't realize this. The Earth is actually precessing. What that means is that as the Earth spins, and I'm not sure which. Well, I'd have to think to figure out whether I'm spinning the Earth in the right direction. Is that right? Might be this way. But anyway, as the Earth spins this way, it also is spinning this way because of precession. That is, over time, the North Pole will become the South Pole. But because it's such a slow thing, it takes 26,000 years for the poles to rotate. It's nothing that we're going to have to worry about too much in our lifetimes. I assume that people won't be watching this video in 26,000 years. Anyway, so precession. Precession is a rotation in the other dimensions as something is rotating in one dimension. It can cause a kind of rotation in the other two dimensions as well. Okay. How do you figure out the angular speed of precession? This is called omega. That symbol on the far left is an omega in Greek. It's a capital omega. And that is the symbol that is traditionally used for precession speed, precession velocity, if you would. If phi is the angle, if delta phi is the change in angle, if you think of the precession circle as a circle, and then the phi is which is the second symbol on top of the second part of the equation, that change in phi per time is another way of saying omega, precession angular speed. Now, we can replace d phi with dl over L. Why? He doesn't explain this. Young and Freedman don't. They don't. But it has to do, I think, with the idea that we're talking radians here. And again, I have a video on radians, and you've already had radians in this by the time you get to this part of the book. Because we're talking radians, dl, the change in angular momentum, divided by L, which is the axis kind of angular momentum, is because of the way radians are, d phi is going to equal dl over L, the change in instantaneous rate of change of angular momentum divided by the angular momentum. You don't have to know why, of course, just memorize the equation. Well, dl dt, that is the instantaneous rate of change of angular momentum per time, is another way of saying torque. And so that's where the torque, the tau z, comes out in the next part. And then I'm left with L at the bottom, Lz, angular momentum. Well, torque equals the weight times the radius of the axis. Because remember, we figured that the angular momentum was r cross weight, r cross w. So we can substitute weight times r for torque, and then we found in a previous video that the moment of inertia times the angular velocity is another way of expressing angular momentum as well. And so basically all of that is to say is that we can calculate the precession angular speed by using the formula WR over I omega. Weight times the radius of the axis divided by the moment of inertia times the angular velocity. So if you didn't understand the explanation, just memorize the equation and apply it. He also doesn't explain why the force of the flywheel toward the center, or if it's a top, the force toward the the bottom, why it's going to be the mass of the flywheel times the omega squared, that is the precession angular speed squared, times the radius. He doesn't explain why. I mean, it looks to be some variation on F equals ma, but he doesn't really explain how omega squared r is the a when it comes to the force that the flywheel exerts toward the pivot. If this is the flywheel, toward the pivot. So we'll just take their word for it that someone smarter than us has figured that out. Now, as omega increases, that is, the faster the precession, at some point we get wobble, which is called notation. That's what torches the rocket in the movie The Martian. Notation, the wobble, because of the spinning. But anyway, interestingly enough, the faster the flywheel is spinning, the slower the precession is. But the slower the flywheel is spinning, then the faster the precession. And that's where you begin to get a vertical component that causes wobble. Okay, well, this has been a little bit on gyroscopes. And basically that if you have something spinning like this, it creates a force of precession like this. Okay, well, thank you very much.